Okay, so you want to build a rocket engine. I want to make this video as a quick introduction to rocket engine sizing that should enable you to size your microliquid project and then gain a better understanding of just rocket engine physics in general. The way I see it, there's rocket engine sizing and there's rocket engine design, and they're kind of separate because rocket engine sizing is describing the abstracted chemical process that represents the rocket engine, while rocket engine design is actual drafting of parts and considering a lot of physical effects on the metals and the construction of the engine. This is kind of analogous to a car engine that has a thermodynamic cycle and then the engine block design. The rocket engine has an isentropic supersonic equilibrium combustion flow and the actual chamber and the injector and everything else that goes along with the engine. So in this video, I'm talking about the cycle. I want to talk about some basic theory, explain the sizing equations, talk about some general trends, and equip you to size your first rocket engine. In the most basic sense, a rocket engine is something that converts chemical stored energy into kinetic energy of a reacting gas. We're focusing on bipropellant liquid rocket engines for this video, although this generally applies to monopropellant thrusters as well, and is tangentially related to solids and hybrids. So let's represent the rocket system on like a high level real quick. So this is half of a rocket engine. The rocket engine is axisymmetric, so this is how I'm going to be drawing it for the rest of the video. On the left, you have propellants, some kind of feed system, the injector, and then the rest is the rocket engine chamber. From left to right, the stations of a rocket engine are called injector, chamber, nozzle, and exit. During operation, the rocket engine produces gas and it ejects it out of the nozzle. The gas has some average velocity, VE, and it also has some pressure, P exit. If you do a balance of forces, you can derive the rocket engine's thrust to be equal to the mass flow rate of the propellants through the exit plane times this average exhaust velocity that is leaving the engine. You also have to consider the difference in pressure. But for now, let's consider the simplified case where the exhaust gases are equal to the ambient pressure. Let's say this engine is operating in a vacuum. Then the equation is just the first term, m dot times VE. This tells us that m dot and VE are very important characteristics of the engine. The exhaust velocity of a rocket engine is also the amount of force over time that it produces per a unit of mass that it uses. VE is the primary performance metric of a rocket engine. It's also called specific impulse. Specific impulse is usually expressed in terms of seconds, which is a nonsense unit, but it's actually just a normalization so that rocket engine efficiencies can be quickly judged across different unit systems. The exhaust velocity is normalized using gravity. M dot, or mass flow rate, is then just a linear scalar of the size of the rocket engine, and in more ways than one. But these are really the highest level characteristics of the rocket engine. How efficient it is and how big it is determines how much thrust you get. Let's talk about some quick examples of some fuel and liquid oxygen combinations and what kind of specific impulses you can expect out of them, given that you're optimizing the engine. So kerosene liquid oxygen usually goes in the 250 to 350 seconds range of specific impulse. Liquid methane is 300 to 380. And then liquid hydrogen is 400 to 460. Now the question becomes, why are they different? Or maybe a better question is, what governs rocket engine efficiency? And the answer is the temperature of the combustion and the average molecular mass of the exit products. So I'm putting up the equation that tells you what the exhaust velocity is based on a bunch of factors. I'm going to partially explain this equation and then we'll come back to it. So the terms that I want you to pay attention to here are the stagnation temperature and the average molecular mass. So T naught and M bar. Everything else in this equation are just gas constant terms, and to fully understand them, we need to establish the assumptions that we're making about the flow inside of the rocket engine. You can see that the efficiency of the rocket engine is directly proportional to the stagnation temperature of the combustion and inversely proportional to the average molecular mass of the gas products. This means that the best engines have the hottest gas and the lightest gas, which is actually why hydrogen wins in terms of specific impulse. Hydrogen combustion products are hydrogen and water, which are very light molecules, and the hydrogen-oxygen combustion has a lot of energy per unit mass, which is why the most efficient chemical rocket engine is the RL-10, which is an expander cycle, liquid hydrogen, liquid oxygen engine, and it has something like 462 seconds of specific impulse. Okay, I'm going to leave the equation for the exhaust velocity up on the board, and we'll come back to it after two things. First, we'll discuss what the rocket engine flow is like, what its characteristics are, and how we can model it. And then secondly, we'll discuss what actually controls these two parameters, what controls the temperature and what controls the average molecular mass in terms of rocket engine design. Because obviously chemistry controls it, but what parameters influence it. And then once we do that, we'll be able to fully understand this equation. So a rocket engine flow for sizing purposes is considered a quasi-one-dimensional isentropic equilibrium flow. So firstly, quasi-one-dimensional means that the flow only varies in one direction. And in our case, this direction is along the length of the nozzle. The reason that it's quasi is because we actually have to consider 2D effects. We consider that the cross-sectional area change, but the argument here is something like that is a function of only x. For sizing a rocket engine, the properties of the flow only change with station or position inside the rocket engine. Now the second part of that assumption is isentropic. Isentropic, if you know thermodynamics, isentropic means that it's an adiabatic reversible process, which means that there is no heat being conducted in and out of the engine, and that there's no change in entropy throughout the engine. Now, you might find this to be a little bit jarring because one of the biggest problems in rocket engine design is the heat that is conducted out of the engine into the either regenerative jacket, ablative liner, or heat sink if you are doing a development engine. The reason that the isentropic assumption holds is a question of relative scales. The amount of heat that is conducted away out of the flow is small enough to where it is relatively negligible. If you're familiar with the concept of isentropic efficiency, which is the difference between a fully ideal isentropic flow and the inefficiencies or losses that occur, a rocket engine's isentropic efficiency is somewhere between 0.98 and 0.95, according to Sutton. We're going to get close to what's actually happening inside the rocket engine if we assume that there's no heat conducted and there's no irreversibilities in the flow. Remember, this is okay for sizing the engine, and then you will stray away from the idealization as you go further into design. The last part of that assumption is an equilibrium flow. This just means that the combustion process is not rate limited by the diffusion or the convection of the gases. So you have an ideal combustion for every position in the engine. This does not imply a full combustion in the sense where you have a stoichiometric conversion of chemicals to chemicals. It just means that there's no time-dependent incompletion. So I apologize if that is a little bit hand-wavy, especially since my explanation of equilibrium flow isn't as great. But let's just keep those three assumptions in mind as we move forward. Flow properties only vary with position inside the rocket engine. Isentropic equations are valid for the rocket engine, and the combustion is perfect. So these are the isentropic relations that allow you to calculate the temperature, pressure, and the density of an isentropic gas relative to the stagnation temperature and pressure, because the whole isentropic assumption basically says total energy is conserved in the flow. You can see this used in the exhaust velocity equation. Now here's what we know about the engine so far. Let's assume that we know some chemical input, and we know what the combustion properties are like. So we know the total amount of energy in the system, and we also know the properties of the gas. We know what the specific heat ratio is, gamma. We know what the stagnation temperature is, T naught. We also know what the average molecular mass is. And we also know what the stagnation pressure is, which is a design point. These properties are known at the chamber. The question becomes, how do I know these properties at the nozzle, at the throat, or maybe at any point in a general sense? This is where the Area-Mach equation comes in. I'm going to put it up here. Okay, so the argument goes something like this. When you have an isentropic supersonic flow, you can reform the relations in terms of the Mach number, because the Mach number is a proxy for velocity and the speed of sound, and it will consistently represent the total amount of energy in the system the same way that it does in the ratio case. The second part of the argument is going back to when we said that the flow only varies with station inside the rocket engine. We can then make the Mach number a function of the cross-sectional area using flow continuity for the isentropic process. So that means, as in the subsonic regime, as the cross-section decreases, the flow speeds up. In the supersonic regime, as the cross-section increases, the flow speeds up. The Mach area relation gives us a function between the cross-sectional area and the Mach number. And because that relation exists, we also have all of the properties of the gas, be that temperature, pressure, or density, as a function of cross-sectional area through the Mach number. This allows us to go from what the cross-sectional area is to finding out what the Mach number at that cross-sectional area is, or finding out what the cross-sectional area required is to achieve a certain Mach number. This is really important for sizing the throat. The throat of a rocket engine must achieve choked flow in order for the transition from the subsonic regime to the supersonic regime to work. This gives us the numerical constraint that at the throat, the Mach number must equal 1. I'm going to draw another rocket engine here. Mach equals 1. This is the subsonic regime, and this is the supersonic regime. But the throat must choke the flow in order for the transition to happen. And so for the Mach to be equal to 1, the area must be some specific cross-sectional area. And this area is called A star, which is the throat area. In fluid dynamics, a star represents some characteristic quantity, characteristic velocity, characteristic area, characteristic length. A star is the characteristic cross-section area that defines the entire rocket engine. The formula for finding out A star is on the screen right now. So the throat area is directly proportional to the mass flow rate of the engine and inversely proportional to the pressure of the engine. Quick note about stagnation temperature and stagnation pressure. We assume that the chamber pressure and the chamber temperature are equal to the stagnation temperature and the stagnation pressure because the velocity inside the chamber is relatively very small compared to the rest of the flow of the engine. So to find the throat area, you need to know what the mass flow rate of the engine is, you need to know what the pressure of the engine is, and you need to know what the combustion properties are, mainly temperature and the gamma. If you go back to the Mach area equation, you can actually see that it's normalized in terms of the ratio between any area divided by the area at the throat. That way, that's where Mach normalizes to be 1. The Mach area relation will allow you to calculate Mach at any point in the engine. And from there, you can use isentropic relations to find any of the properties that you want at that location. So in terms of general trends, you will see that temperature will do this, pressure will trend like this, and then the exhaust velocity will trend like this. Okay, now that we understand the Mach area relation, let's go back to the velocity equation and talk about the two other parameters that determine a rocket engine's performance. And those two parameters are the pressure, the chamber pressure, and the oxidizer to fuel ratio, OF. So in general, for any combination of propellants, increasing chamber pressure will increase the efficiency of the engine. So if we plot the exhaust velocity on this axis and chamber pressure on this axis, this is what happens. Increasing the chamber pressure increases combustion efficiency, but it also increases the heat flux into the engine by increasing both the combustion temperature and the convective heat transfer coefficient from the gas to the chamber wall. And it also increased the hoop stress on the engine, making the material requirements harder. For every pressure, there's some ideal oxidizer to fuel ratio. Now the curve for this actually looks something like this. And this ideal oxidizer to fuel ratio will depend on the chemistry and the pressure. When the ratio is really low and the combustion mixture is very fuel rich, which is this direction, the combustion temperature is low. But as you go more to the oxidizer side, the temperature increases. This is familiar to you if you know about car engines. But the other effect that happens that isn't proportional to this is that the average molecular mass is also low on the fuel side, and it becomes high on this side as well. So if you remember, efficiency is good when you have a high temperature and a low average molecular mass. So there is some ideal OF ratio for each pressure that maximizes this effect of T naught over M bar. Now here's the problem. I'm talking about an ideal OF ratio. Don't think about it as related to some stoichiometric mixture. You will actually hear this idealized OF be referred to as a stoichiometric oxidizer fuel ratio by some people in the industry. But this term is confusing because it does not describe a stoichiometric mix in terms of this many molecules of oxidizer to this many molecules of fuel that yields some combustion products. You really should only think of the ideal oxidizer fuel ratio as where this ratio is maximized. This will vary significantly by chemistry. So for example, hydrogen, because hydrogen is such a light molecule, the ideal oxidation-to-fuel ratio is very biased towards a fuel-rich mixture by let's say kerosene standards. It's in the 5-to-1 range, but we describe things that are more than 5-to-1 as oxidizer-rich and things that are less than 5-to-1 as fuel-rich because of this ideal oxidizer-to-fuel ratio. For kerosene, especially in our pressure ranges, it's closer to it's around 2.5. And for other propellants, it varies. The practical way to find the ideal oxidizer-to-fuel ratio is to do a parametric study in a combustion solver like CEA, where you specify some fixed pressure that you have chosen, which is your design parameter, and then you vary through a range of oxidizer-to-fuels, and then you'll see a plot like this, and then you'll choose your ideal oxidizer-to-fuel ratio for your rocket. The same way that running a higher pressure engine is better for efficiency but harder to build through an increase in temperature, an increase in convective coefficient, and an increase in hoop stress. Likewise, running at an ideal oxidizer-to-fuel ratio is the best for efficiency, but it might be hard to build. So potentially one strategy is to run fuel-rich, because small decreases in oxidizer-to-fuel ratio will yield small drops in performance, but will significantly reduce the flame temperature, because it's not just the flame temperature that it adjusts, but the ratio of the two. This is something to consider, but when sizing your rocket engine at first, you should find what the ideal oxidizer-to-fuel ratio is and size it off of that. Okay, the last two things that I want to talk about are some other parameters of the rocket engine that matter for sizing, how to make the contour, and then how heat flux varies throughout the engine. So to size the engine, you will need a parameter called L star. It's characteristic length. This is an empirically derived coefficient that tells you how big the combustion chamber should be for any given chemistry. The way that L star is defined is that it's the volume of the chamber divided by the A star. So if you want to know what the volume of your chamber is, once you've selected your throat area, you'll go and look up what the L star is for your propellant combination. For us, it is kerosene liquid oxygen. So our L star is about 1.1 meters. And then you roughly know what the volume of your engine should be. L star is a proxy for combustion residence time. Remember that when we were discussing the assumptions of the rocket engine, we made the equilibrium combustion assumption. L star basically says this is approximately how long the engine needs to be to get into the range of the combustion has enough time to finish. If your L star is too small and your engine is too short, you will start to significantly diverge from the equilibrium assumption, and the propellant will be leaving more unburnt than designed. Going higher than L star will give you very, very small additions in efficiency for very large penalties in terms of weight and total heat. Another important performance characteristic of a rocket engine is called C star, which is characteristic velocity. Now remember when I said that the exhaust velocity is the primary performance metric, and it is for the idealized chemistry. The characteristic velocity of a rocket engine is defined as the stagnation pressure times the area star divided by mass flow rate. This serves as a proxy for combustion efficiency and injector performance. So your injector will not fully mix the propellants, and your combustion will not be fully equilibrium. So when you have a test fire and you measure the C star, all of these parameters are easily measurable. You can measure the throat area with calipers, which is important, especially if you have an ablative nozzle and you have some kind of erosion. You can measure the chamber pressure with a pressure transducer, and you can measure the mass flow rate with a Venturi or a flow meter or something. And then you'll get some actual C star. And then when you divide by the ideal C star, you'll get some efficiency of the rocket engine, and you want to be maximizing that as much as possible. If this ratio is low, that means your injector is bad or your combustion is not complete for some reason. It's a very good metric for how close to the ideal sizing your actual rocket is. A similar purpose is fulfilled by the coefficient of thrust, but that is more important for solid rocket motors, not as much for liquid rocket engines. Okay, so you've sat through this entire video, and now how do you actually go about making your engine? So I'm going to go through this step by step. I'm going to tell you roughly how you could do it by hand, and I'm also going to introduce you to a couple of softwares that you can use to help you out here. So our number one step is to choose propellant combinations. If you're participating in the microliquid challenge, this is already chosen as kerosene and liquid oxygen. Your second step is to choose two of the following three characteristics: chamber pressure, thrust, or mass flow rate. Choosing two will constrain the third, and when you're sizing a vehicle, usually you have a thrust requirement and you have a pressure requirement that is driven by your metallurgy or your efficiency requirements or something. So the mass flow rate is therefore determined by that. Once again, for microliquids, the pressure is already set at 500 psi, and the thrust required is, I believe, 50 pounds. You can calculate what mass flow rate should be once you do the combustion chemistry and find out what VE is. Step 3 is to create a chemical profile for your engine. This is where you use an equilibrium chemistry solver. I recommend NASA CEA, although you can also do this in RPA, but we'll come back to that when we go to the less manual approach. In the manual approach, you'll use NASA CEA. In NASA CEA, you'll do a rocket-type combustion solution, and you will input all the parameters that you know. For your exit pressure, you'll want to use either atmospheric pressure if you're designing for a static test fire, or the general rule is 2/3 of the pressure range PC minus P highest in terms of expansion. This kind of goes into vehicle dynamics, but don't worry about it. Choose the exit as either atmospheric or like 3/4 P atmospheric. You'll have to do a ratio, but you can figure out how to do that. Then lastly, you'll want to do that parametric oxidizer fuel ratio study where you vary for your pressure from some low oxidizer fuel ratio to some high oxidizer fuel ratio to find out what your best efficiency is. Again, for microliquids, you're in kerosene and you're in the 500 psi range, so you'll be varying it from 2.0 to 3.0. Do it with approximately 0.1 increments, and then you'll get a pretty clear picture of what the ideal should be. Once you've run your CEA, you'll want to export it into Excel. The way to do that is to go to tabulate my data, and then you'll get a list that goes like this. You'll have a bunch of parameters. Choose the parameters that you think are important based on the equations that we discussed. And then you'll get essentially stations. So you'll have chamber station, throat, you'll have exit, if we're choosing an infinite combustor, which we are for now. And then these will repeat one over the other if you chose different OF ratios. So figure out how to plot what you need to see the relationships, to see the trends that you're looking for, especially for that oxidizer to fuel ratio optimization. And just play around with the data. This is the best way to learn, is to nudge things and see how it affects other things and have some fun. Cool. So once you've chosen your OF ratio, you'll also know your mass flow rate based on that. And now you have everything that constrains your engine, basically. Step 4 is to find out what your A star is based on the equation you have. Once you have A star, you can use the area expansion ratio, AE, to find out what your area exit is. And then you can use a standard contour shape. I recommend looking up the one in Sutton, but basically a rocket engine is a line, an arc, a line, an arc, another arc, and then a line. At first, I recommend using a conical nozzle because at low pressures, the efficiency gains that you'll get from a parabolic nozzle are going to be very slim because it'll look basically like this and there's very little difference. But you can read up on parabolic nozzles in Sutton as well or some other text. Remember, parabolic nozzles are a mass optimization. And then standard ratios for this and for these two can be found in Sutton as well. At this point, you should already have the area here and the area here. You'll find what this angle is as well, and you'll be able to find the length if you want. And then you can choose some contraction ratio, usually like 3 is pretty good, between A star and this, and then the length will be governed by L star through the volume relation that I showed you above. And that is basically your rocket engine. That's what goes into sizing the rocket engine. This represents the idealized shape and the idealized chemical process that makes your rocket engine work. Now, you can do this by hand, but if you want, you can also use our own Liquid Propulsion Group rocket configuration visualizer, which will basically do this math for you and export it into SolidWorks. Or you can use a commercial software called RPA, which will allow you to use a trial version. You just have to restart it every like 3 times, where you'll be able to do actually this entire process in that engine, in that software, and it'll also give you a contour. I just find it to be more interesting that for the first time, at least do it in Excel, see the trends. Then you can maybe either use our software to plot the contour or RPA to plot the contour. One last parting remark is how heat transfer varies throughout the engine. So the heat flux in the rocket engine will roughly look something like this, with the nozzle experiencing the worst heating by far. This is HG and actually just total Q. The boundary layer heat transfer physics are kind of complicated. However, we can estimate the rough heat transfer using something called the Bart's approximation, which is an empirically derived equation that has been used in the industry for sizing, not necessarily for final design. I'm putting it up on the screen now. The rocket configuration visualizer implements this code, and you can go plot this curve for your engine, or you can go to RPA and it will also implement this or a different estimation as well for you, and you'll be able to see what the heat transfer is for your engine. The heat transfer is really important if you're designing a regenerative jacket, and it is somewhat important if you're designing an ablative engine. But at the hobby scale, an ablative engine will generally be okay even without fully knowing what the heat transfer should be like. You can also implement film cooling and things like that to decrease boundary layer temperature, but that is a discussion for the design, not necessarily for the sizing. One final note about the heat transfer is that there's a lot of this big asterisk above this, but in general, the radiative heat transfer regime matters a lot in the chamber and doesn't matter as much in the nozzle. The primary effect for this is that the chamber temperature can be like 3000 Kelvin, where there's a lot of radiative heat transfer, while in the nozzle it drops off significantly, and also so does the density. So keep that in mind. All right, cool. So we went over high-level rocket engine concepts. We talked about how gas properties vary, what the assumptions are. We talked about the Makar equation, which is really important. We talked about the isentropic gas relations. We talked about what governs the exhaust velocity in a rocket engine. We talked about how chamber pressure and oxidizer fuel ratio affect rocket engine performance and other characteristics. I included a step-by-step guide on how to size the first rocket engine, and we talked a little bit about some heat transfer stuff. Hopefully this is a good introduction to sizing your first rocket engine. Feel free to reach out if you have any questions, and get started on the CEA steps that I showed you, and also get access to a copy of Sutton, Rocket Propulsion Elements. Rest in peace, Sutton, but he is still helping you design rocket engines and gives you a good overview of a lot of things. Good luck. Goodbye.